All right. You guys with me?
Yeah.
Okay. All right. Today we're going to do lie detector. And the reason we're doing lie detector is not because I expect you necessarily to be, you know, the chief engineer for the CIA at some point in the future, right? The reason we go through all these examples is because they sort of teach you general lessons, right? That then you could apply to everything. And so I want to put over here the tools that we have already, that you already have in your pocket, right? And I'm going to show you how the tools that you already have allow you to address what a lie detector is, right? So, I mean, I'm sure everyone's familiar with lie detectors because you always see them in like movies, right? And so there's like the detectives, and then there's the suspect, right? And they connect him onto this machine. You guys know what I'm talking about, right? You've seen those shows, right? And what do? Remember usually how does it play out? Yeah?
Doesn't it like test how much you're moving to see if you're nervous, you move more, and it goes on red or green?
So if you're nervous, maybe you're shaking a little bit, so it's a motion detector is one hypothesis, right? What else? That's not a bad guess. Yeah? Maybe it measures your heart rate, right? Because if you're putting something on someone's body, right, then their heart rate might go up. That's a good maybe. You guys should go work for the CIA. Any other, and those are, by the way, good ideas. They're not going to be the type of lie detector I'm going to show you today, though. So I'm not saying they're bad ideas, but what is another way you might be able to tell them? Yeah? If you're what? If your heart rate is fluctuating, yeah. If your little sister stole your candy bar, right, and you're staring at her, right, and you're saying, "Did you steal my candy bar?" right? What would you be looking for that might tell you that she was kind of guilty? Yeah.
She doesn't want to make eye contact.
Doesn't want to make eye contact. Couldn't make an eye contact. Anything else? Obviously, there's one answer I want. You're giving me very good answers, but it's not the answer I want. So I'm like fishing it out. What else?
The hands are kind of like this.
Hand position. Okay. Keep going. Okay.
They have maybe a shallow breath.
Shallow breathing. So you can make a breathing sensor. We'll do breathing sensors as well. Yep. But all very good. Unfortunately, still not the one I need. Yes. Sweating. Maybe they're sweating.
Can we get a hint?
That was a good hit. That was where we are. That's where we're at. Specifically, the notion is that when you are anxious, you sweat. And in fact, that sweating causes a change in your body resistance. So that's what we're going to be going after. The notion is, and I'm going to use an arm. We have the arm. And I want you to imagine now that the arm is a resistance. Can you see this color here? Fine. And so I'm going to call this R body. And it's the resistance of the body that we are going to hypothesize changes when people lie. Meaning specifically when they lie, they become sweaty, maybe hot, all right? And that's what we're going to go after. Not that all the other measures you're talking about are not valid, right? I think heart rate and all that is very good as well. So it's a resistive sensor, and so we're assuming that the resistance of the body is a function of whether or not they're telling a lie or not. And so this is, in a sense, our sensor. Let's go back to how we conceive of every biomedical instrument, right? We have our circuit, And then coming out of it, we have our sensor. And then here, obviously, we have our display. Okay? And the sensor is the key element because the sensor converts the measurand into an electrical quantity. If you don't have a temperature sensor, you don't have a temperature measurement instrument, right? If you don't have a pressure sensor, you don't have a pressure measuring instrument, right? So what we have here is something that converts, and again, very the quote line, into a resistance. So it converts what is the measurand into an electrical quantity. It's a little bit different though than what we talked about before because now the resistance is the person, right? That's why it's a bit odd, right? It's not a thermistor, it's the person, all right? Interesting, okay? But let's keep going. So now, well, there's always wires running out of the sensor, right? And how many wires? Well, there's two, right? Always two, right? Maybe sometimes more. And so we're going to have two wires running here. Now what we're going to do is I can't insert a wire. We're not going to insert a wire into the body, right? We're going to take a wire and we're going to touch it here. And we're going to take another wire and we're going to touch it here. And where the wire touches the body, as we discussed before in the EKG project, right, is in fact going to be called an electrode. It's going to be two of them. And I guess you would need to imagine maybe nitrogen that this entire combination here of the electrodes and the device somehow forms the sensor, right? These are just wires touching the body. Instead of using wires, however, you could use, we have them right here, right? You could use these, right? These are the electrodes, right? So, you know, you have the suspect there. It's kind of maybe not great to have your assistant hold wires to their hand. It's not going to be very stable, so you might stick these on their hands, right? And they don't know what these are, so they're getting very nervous, right? And so we might have these electrodes stuck here and stuck here. Okay. And now we have effectively we have our resistance. All right. Well, I need a circuit, right? I mean, I'm looking at the suspect. I cannot see their resistance. I cannot see the resistance on the end of the wires, right? So what circuit do we use? Do we have anything in our toolkit that we could use? Hint, there's very few circuits we use in this class, right? It's one of them. Voltage divider. So here we have our tool of the voltage divider. And lo and behold, that's the circuit for this. Wow, see? You already have all the information you need. So what we're going to do is I'm going to add a battery here. I'm going to add a resistance here. And I'm going to complete the loop like that. Right? So this would be V. And this here is R fixed in the sense that right? We know what it is, right? It could be 3 ohms, it could be 2 ohms, it's not changing. This is very similar to what we've done before. The only difference here is now your little sister is in the circuit. Does that make sense? And now we need to measure the voltage. I'm going to measure the voltage. We'll measure it right here. We'll measure it between this point and this point. So I'm going to call this V out. And we have our voltage divider equation is equal to R body over R body plus R fixed times V. And so what do we know? Well, we know this. I'll put a line over it, right? Because we picked it, right? We know this because we picked it. We know this because we are measuring it. So it's really one equation with one unknown, just like before, right? So now you got your resistor, and you got a battery, a 9-volt battery, and you got a 1K resistor, and you got some wires, and your resistor is in the loop. And you are measuring the voltage. And you're going to tell her, you think I can't figure out if you took the candy bar or not? You're in trouble, because I took biomedical instrumentation. Yeah. Yeah.
A while ago, we had talked about how the length of the resistor can affect the resistance. So is it like the distance that you put the electrodes on?
Yes. So the question is, you're going back to a situation where we talked about that the resistor, if you want to understand the resistor as a physical object, right? The resistance is equal to what it's made out of times its length divided by its area. So if we imagine that your sister's arm is like this, then your point is, well, but wouldn't the resistance I measure depend on where I put these electrodes, right? So let's talk about exactly that problem, right? So let's come up with some numbers. We're going to make it easy. So the voltage we put in was 10 volts. And the R fixed was 1 kilo ohm. I need to go to these bigger numbers because it's more like what you're going to see physiologically. And you measure out 5 volts. So in this case, if you wanted to know what our body is, hopefully you can see that when you have 10 volts, right, to get 5 volts here, it means you have an even split, right? It means that this quantity here is a half. So that's why I can just quickly get to the point that I know that this is 1 kilo ohm, right? Because 1 kilo ohm over 1 plus 1, that's where I get the half. You're with me, right? Okay, so your sister's sitting there. You hooked her up. You measured 1 kilo ohm. She lying? I don't know, it's one. So we're going to say that when you lie, your resistance decreases, right? When you lie, your resistance decreases, right? Well, she's at 1 kilo ohm. Did she take your candy bar, right? The last 9 times she did, but she swears that this time she didn't, right? Well, what does this mean? We have a problem because you don't know, right? I'm asking you a question you don't know. What is 1 kilo ohm? Now to Adrian's question, we have a bigger problem, which is, well, what if this was moved? I'm going to try to use another color here. It's going to be a little messy, but let's say we put this line here, right? So your sister says, oh, I don't like how this feels here. You move it to the other location. So now they're closer together, right? If we were to accept this situation here, right, the resistance of the body would be different, right? Because we're measuring from, it's like having a shorter tube, right? So if you do this, I'm going to put this in green. Here, the resistance of the body is in fact 0.5 kilo ohms, right? And you would know that because you would have measured a different voltage out, right? So if you did this, you would have measured a different voltage and then you would have calculated this, right? So she can have a resistance of 1 kilo ohm, right? She can have a resistance of 0.5 kilo ohm. And in fact, she could have a resistance of 2 kilo ohm, right? You can't tell from the resistance what's going on. It's your point, right? I mean, if you had measured, what if her right arm, what if she's wearing sunscreen on her right arm? You put it on her right arm. Now it's 10 kilo ohms. She lying? You measure it on her foot, right? It's 3 kilo ohms. Then for me, there's something missing here, right? And what's missing here is usually when we have an equation like something like this, it usually needs to come, I'll use this, right? It needs to usually come with an equation. An equation such as, for example, RT is equal to alpha times the temperature, right? Some equation, right? We've always had those equations, right? Now, there's been some variations. If you go back to the EKG, it's more like a 1-to-1, right? But if I gave you the thermistor project and you didn't have this equation, you'd be in the same situation, right? I don't know. I give you the thermistor problem. You measure 3 volts. Is it hot? Is it cold? You don't know. And in this case, I didn't give you this equation, right? In fact, I don't know how to give you this equation. I don't know what your sister's resistance is when she tells the truth, and I don't know what her resistance is when she lies. I don't know, right? I don't know. What do you do? And here you might have the answer because you've seen the detective movies. They don't, so what do?
They ask like baseline questions that they know the true answer for, like what color are your eyes?
Yes.
What is your hair color?
So repeat, they ask baseline questions that they know the answer to. Like what is the color of your eyes? Or what's the other example? Say, what's your birthday?
Or your hair color.
What's your hair color? So your sister's sitting there. What are the color of your eyes? It gives you an answer, right? So you ask her, right? You ask a question, whatever it is, a question you know the answer to. And she gives you an answer. And you measure 1 kilo ohm, right? Then you ask another question, right? Like, do you love mom? 1 kilo ohm. Right? Do you go to school? 1 kilo ohm, right? And then you get to the question that you're interested in, right? And that question is, did you take my candy bar? So now you ask this question, I'll put it in red, and now you see 0.6 kilo ohms. Interesting, you say. And then you ask her something else, like, is your room smaller than mine, right? She gives you 1 kilo ohm. Right? Maybe you ask her something else that you know she's going to lie on, right? Like she always lies about going to bed early. Did you go to bed early? Yes. 0.6 kilo ohms. Right? Right? So that's what they're doing, right? They're trying. And this is something that has a name, though maybe it's weird to call it that, but it's actually something that you have done before. Have you ever been in a situation where you weren't sure about the equation? Hint, thermistor lab, right? You weren't sure. You had an equation, but I told you, you better not quite trust it, right? So what did you do? Was calibrate. Right? A calibration, right, is when you have a situation where you take sort of known quantities of your measurand, like a 10-degree glass of water and a 20-degree glass of water and a 30-degree glass of water, right? And you just get the values. 10 degrees is this, 20 degrees is that, right? Here's the same calibration, only we're doing it for truth and lie. Yes?
So if the premise is that it lowers because of the sweat doesn't go away like after you tell a lie.
Right, so now you're getting more detailed. What if she lied here, but then it goes back?
We're suspending her disbelief.
So, well, let's talk about it. This technique is not perfect, So there might have been some carryover effects. So let's deal with that, and I'm going to give you a little bit more sophistication, right, about how we can make these better lie detectors. But it's a perfectly good concern, right? Now but of course you can check it, right? If you think about it, you could go back and say, what's your hair color? And if it's still at 0.6, right, you'll know, right? So there are ways to potentially address it. Maybe that's, no, now you have to be a good detective, right? And kind of figure out what you're doing. But there we go. So this is tools. This, same old voltage divider, same old calibration. So you see, you already knew, because you already had the tools. I didn't introduce any new tools, right? There is a little something extra that I want to mention, because it's going to come up later. I guess we don't need this extra line anymore here. Well, I just want you to note that your sister does not radiate resistance. And the only way we were able to get resistance out of her was actually by putting current into her body, right? She is now not just sort of a passive observer, but we're actually putting energy into her body. And that's going to be an idea that's going to play in another second, okay? All right. But I think for now that we don't have to update that. So you're feeling pretty good. You're about to make the final accusation, like at the game of Clue, right? Where you're like, that's it, right? Show me where the candy bar is, right? She's getting a little bit uneasy, right? You ask her another question, like, is our dog's name Cutie? She says yes. And then, without you even asking her another question, she kind of fidgets a little bit. You know, she kind of moves around a little bit. And all of a sudden, here she moves. And the resistance goes to 5 kilo ohm. She moved, right? Something happened here a little bit, and she moved a little bit, right? And now you're thinking, oh wait, but she didn't lie, right? There's I'm making, the room's hot, right? Everyone's, it's a kind of a hot room, right? Because you've decided to set up an interrogation facility in the closet of your house to really, you have the light shining on her, right? Those lights, it's hot. And even you're feeling hot. And as it gets hot, you notice that it, let's see, I'm going to make it go up. That all of a sudden the resistance becomes 2 kilo ohm, right? And now you're getting a little bit uneasy about these accusations because you realize that there are other things that show up as the output of your device. And we have a name for those other things, right? What do we call those other things? Noise. So we know that we have signal and we have noise. Now, signal is simply the thing that you wanted to measure, and noise is everything else. Now, if the purpose of the project was to make a motion detector, then this would be signal. And if you were making a temperature detector, then this would be signal. But it isn't in this case, right? And you already know where is the noise creeping in? At what point is it being introduced? Is your voltage divider? No, it's at the sensor. It's always at the sensor. So this sensor, maybe because it's on her body, right, is sensitive to motion, right? Or maybe just her getting hot because you're shining these lights on her, right? It's just, well, it's changing her resistance, but it's not related to sweating. It's just that she's getting hot, and that's changed her body resistance. And of course, the problem is now you don't know. I mean, the issue with signal to noise isn't that there is signal to noise, is that you don't know, right? This was our key question right here. And now the question is, did she lie? Or did she move? What's that? And it could be both. They could say, well, one way to deal with that is I'll ask her 3 times or something like that, right? But it's worse than what I've shown you here. So this is an ideal situation. You're not even going to get this. I'm sorry to tell you. This is what you're really going to get. We'll delete this. Because in biomedical engineering, things never work out easily. So you start with the initial question of what is your hair color? She gives you the right answer. You have a different answer. You get 2 kilo ohm. But then you haven't asked her anything else. You're just sitting there watching it, and the value becomes 3 kilo ohm. Okay? You're not asking her anything. You're just kind of looking around. You're waiting. Now it goes to 1 kilo ohm. And then it's back to 2.5 kilo ohm, and so on. It's unstable, right? So it's not the way I showed you before, where it's like somehow it only resets every time you ask a question. It's actually resetting all the time. If you were to plot this over time, where this, let's say this is the R body, or what you think is the R body. Maybe you start seeing, and again, this is without asking any questions, right? It's just, right? It is a naturally unstable situation. Because these noise inputs, I'm telling you right now, it's not like the noise is waiting and then every time you ask a question, the noise is like, okay, now we're going to mess it up. It's constantly messing up. And this is exactly what you're going to see if you try to do this experiment on your sister. It would not work because these other sources of noise are very bad. In fact, if you were to really zoom in, I'll do this in green, not only would you see this noise, maybe you would see, well, no, I wouldn't say that. Okay. This is the actual situation that you're in. These contacts are too loose. She won't stop squirming. There's a draft. There's a million things that are making this very hard to detect, right? And in fact, when you're doing your EKG, when you piloted your EKG, I know it was a little bit different, right? But when you piloted your EKG and you looked at the signal on the screen, was it like this? No. It was moving all around, all right? It was always moving all around. These sources of noise are very problematic. All right. Well, what is a tool that we might use to address this issue? What do you use for your EKG? What's the next tool you would use? A filter, right? So, filter. However, for a filter to work, the signal and the noise have to be at a different frequency, or at different frequencies, right? We spent a bit of time on that. So if the signal is at 1 hertz and the noise is at 100 hertz, we're good. But I'm going to tell you right now that this noise is all over the place. You're looking at it, and it's, and not only that, but like you don't have that ability here. All right, it's drifting sort of slowly like this, and there is no, and we could talk more about it, but I'm going to take that option off the table. This is just, let's just assume that this has all frequencies in it. and you don't even know exactly what is the frequency of the signal, is also a bit unclear to you, right? Because it's sort of she lies, and then it sort of changes slowly. So you might consider a filter, but it's not going to work in this case. And you're sitting around and you're thinking, man, I wish I could use a filter because filters are really nice, but the signal and the noise are not, right? They don't separate it out, right? What if you had a magic wand, which I'm going to give you, and that magic wand takes the signal and makes it any frequency you want? So you could say, I want my signal to be 1.1 kilohertz exactly. And it makes you the signal at 1.1 kilohertz. And now it's going to be very easy to filter it because you literally put the signal wherever you want. How do you do that? The way you do that, and again, this is not about lie detectors, to be clear. This is a general trick in biomedical engineering, okay? In general in sensing, is that instead of using a DC source, which is what sort of I assumed before, maybe it was a, right? We're going to put in a sinusoid of a known frequency. What will happen? Let's think about it. We can approach this with sinusoidal steady state analysis, but I don't really think we need to because it's just resistors here, right? So I can simply take this equation here and rewrite it now as, I'm just going to leave it here. I'm going to rewrite it as, I'm going to replace V with the sinusoid that I'm putting in. And let's say that sinusoid has an amplitude A, right? And it has a certain frequency. We'll start talking about the angular frequency in W, right? And so we're going to have A cosine of WT, right? And that is and so this is our input. This is what we sometimes call the transfer function, and this is the output. And the output is simply, well, the output is going to be V out is equal to B times cosine of WT, to be clear, where B is our body. I mean, you can see this, but I'm going to write it out, over our body plus our fixed times A, right? Remember, sinusoid in, this is now the input of the circuit, sinusoid out. That's one of the big rules of sinusoidal steady state analysis, right? Sinusoid in, sinusoid out. Are you with me on this? So that's why when we put a sinusoid in, we have to get a sinusoid out. What is the frequency of the sinusoid out? It's the same frequency as the sinusoid in. The only thing you can do in the game of sinusoidal steady state analysis is change the size of it. So whereas the size of the thing coming in was A, the size of the thing coming in was out was B, and B specifically is given by this, right? The voltage divider. Now let me draw it out. What is happening here? Okay. First, let's look at our body. Let's just remember, which, you don't know, but I know it because I'm making it up, right? And let's say that our body is at, we'll call this 1, 2, 3, 4, right? These are the kilo ohms here. And again, it just is for just example purposes. Let's say it started at 2, then it went down to 1, and then here goes up to 4, for whatever reason. All right? That's what our body is doing, maybe whatever reason, right? She's semi-lying, really lying, telling the truth, something like that. All right, now let's look at V the input that we're putting in, right? This is the input that we're putting into the circuit. This is the battery source here. So let's draw that on the same axis. Boom, 2, 3, 4, 5, 6. So this is the amplitude of the sinusoid. And I'm going to put 0 here. Up, down, up, down. In fact, we know that it's, A to minus A. And let me draw that in orange or some color here. So this sinusoid here, and I'm going to try to get a few cycles in, is doing this. I'm going to have to go all the way across, okay? Okay. The question is, what is V out? No, didn't quite align it. Okay, what is V out in this case is really what I want to understand. Well, let's think about it. Oh, and I'm also going to give I'm going to give us the R fixed, because I'm just going to make this example easier to understand. I'm going to make R fixed 2 kilo ohm, just for this example. Okay, now let's talk about this period first. Right? In this period of time here, our body is 2 kilo ohm. Now R fixed is 2 kilo ohm. Right? So we have 2K and 2K. It's actually an even split, right? Or 2 over 2 plus 2, which is a half. So during this time period here, because the resistance of the body is fixed to here, this is actually reduced by half, right? It's like putting a 1/2 multiple on it. So the output, if I were to use the same scale here, 1, 2, 1, 2, I'll do the output in blue. I don't think we need to make colors. I'll do it in this color. Is going to be what I've done here is I've tried to match up, this frequency should be the same as this frequency. I've tried to do the same number of wiggles, but I've tried to, in my illustration, point out that, if I'm doing this on the same scale, that the wiggle is half as small. Okay. Let's talk about here. So here, okay, now she's lying or something, or more lying, right? So now she's at 1 kilo ohm, right? So I have 1 kilo ohm. This is still 2, right? 1 and 2. I have a voltage divider. So I have 1 over 1 plus 2, right? Or 1/3, right? So at this point, well, because remember, voltage dividers are always about splitting the voltage, right? And this one just got weaker, so it's getting less of the voltage. Instead of being half, it's now 1/3. So what that means is that from this period to this period, I'm applying 1/3, right? I'm multiplying this by 1/3, right? I know I know you're tracking it. I'm just deliberately doing it super, super slow, right? Okay. So 1/3 of A instead of half of A, I don't know. I'm just going to draw it smaller. So it's going to be, see, that's supposed to be smaller, right? Now here, something happened again. Here, her resistance went up to 4. Let's say she's super telling the truth about something. So now I have 4. This is still 2. Right? So now I have 4 over 4 plus 2, right? 4/6 or 2/3, right? So that's more than a half, right? And so from this point on, I'm going to exaggerate it a little bit, but I just want to make it clear, it's bigger. What I want you to pay attention to is not the wiggling, but the size of the wiggles. And you can do this on the top, or you can do this on the bottom, which also would be called the envelope, for whatever reason. And let me also draw and this is, the zero, right, is here, right? This is all around 0. It's a sinusoid, right? So you could have done the envelope top, you could have done the envelope on the bottom, you could have done the envelope from the top to the bottom. What you can see is that the envelope tells us what the resistance is. For example, if I said at some time point here, right, now I don't know the resistance, so at some time point here, it is now, it goes back to this value, right? So at this time point here, right, it's back to half. Well, you know that the resistance therefore went back to 2, right? The size of the envelope tells us the resistance, not the rate of wiggling. The rate of wiggling doesn't, because the rate of wiggling is just what we, right, put in, right? It is the size of the envelope that betrays what our body is. Yes? No noise here yet. I'm going to put it in a second. And this point is perfectly clean. So the size of the envelope tells us the resistance. So as long as you can read this wiggle, you can know. So far, so good. Why did we make it more complicated? Right? Why did we make this more complicated in this case? Because now let me introduce the noise. I'll use user space here. Okay. So now I'm going to introduce the noise. I'm going to call this R noise. I'm going to put it on the same axis. And I'm just going to throw it into some arbitrary units. And I'm going to say that the R noise is, let's say it starts off as nothing. And then it, I'm going to call it actually, and I'll justify this in a second. I'm going to call this V noise. I'm going to say that the noise is actually being introduced as a voltage, not as a change in resistance, and I'll explain this, okay? But for this point, I want to just do it this way because the example is going to be easier. And so the V noise, initially there is no noise, and then the noise becomes really big, and then it goes back to 0, and then it does this. Now, I mean, that's a very odd thing for the noise to do, but I'm trying to do it here for cartoon purposes because I'm going to now be measuring here. My V out is going to be corrupted by the V noise, right? I'm going to have to add them together. So to be clear, this was V out with no noise, right? Just a signal, if you will. The combination of the two, which I've left myself just enough room for, because I want it all to line up, 1, 2, 3, will look something like this. So it's going to be V noise plus V signal. Let me use the, use this color. It's going to look like this. It's going to be this plus that. So it's going to look like this. So I'm drawing a medium-sized wiggle, and then it's going to jump up here. This could be a little wiggle. Did I happen to align it? Fine. And then I'm going to drop down here. I'm going to do a big wiggle. And then here, the wiggle is going to start to sort of take this little ride up and down. I didn't draw that great. Here, what I wanted to show you is that the wiggle was protected. Here, I have my little wiggle, right, plus an offset, right? But notice, my little wiggle is still sitting there, just offset, right? And then here, I had my largest wiggle of all. That's this wiggle. So the wiggles are riding on top of the noise. But you know, like if you look at, for example, from this period to this period, right? Your sister's resistance did not change. And if you're looking at this, you also know that her resistance did not change. Because you know that this is not her resistance changing. Her resistance changing is only at the wiggle, right? Everything from your sister is at this wiggle rate. And we're going to call this, in this case, the carrier frequency. Because engineers always have to name things, okay? That's the, yes? It depends on the it depends on the nature of the noise, right? And so let me I want to directly address that, but I'm going to convince you that the nature of the noise is going to show up as a voltage and is not going to be showing up as a change in resistance. It's not entirely true, but I'm going to justify that to you. And I'm obviously I'm trying to set up the problem in a particular way, but I can't justify it. Should I just justify it already? Let's just do it. All right. The noise is being introduced to particularly at the electrode, right? How do we model the electrode? Well, we model the electrode. If we were to zoom in on this electrode right here, right, the way we modeled it before, we modeled this electrode. Maybe I'll keep it as a circle. As a battery that's producing some noise plus a resistance that's producing some noise. Right? A battery that's producing some noise and a resistance that's producing some noise. So this contribution here is a voltage addition, right? And this contribution here, right, is a resistance addition, right? So the question is, why am I preferentially? So it doesn't seem to have solved the problem, right? I'm going to suggest that this can be relatively minimized compared to body resistance. You may say I don't accept it, but I'm going to say that if you use this, all right, if you use something like this, all right, it will reduce this to the point that it's less negligible, but we can never get rid of this one fully. The gel will reduce both, but again, this one is just one we can't actually get rid of fully. In fact, all right, let's unpack that some more, and then we'll go back to this. Well, what I'm going to eventually tell you here is, therefore, all you need to do is band pass this at the carrier frequency, and it's perfect. For example, if you had selected this to be 2022, right, then guess what? Your signal is at exactly 2022 hertz. And therefore, if you filter at 222 hertz, the only thing that's going to come out is your signal. So that is the magic wand, where we make the signal any frequency that we want. Now I'll come back to that. Let's talk a little bit more about the source of noise. Let's say you wanted to measure your sister's heart rate, but you were going to put the electrodes on her arm. It's a little hard, but that's what you wanted to do, okay? So you'd put the electrodes on her arm. Let's go to this, where could we put it here? So we're back to your sister's arm, 1, 2, 3, 4, 1. And you put 2 wires on her arm, and your goal is, in fact, to measure the EKG on her arm. And that's sort of how you would do it, right? You would put 2 electrodes on her arm, and maybe it might be better across her chest, but you can actually do it. Let's say
Would you put the electrode on, like right on your vein or something?
you can maybe come up with, maybe, I'm not sure, right? Somehow that would pick, I'm not sure that would help, maybe. Let's say you wanted to measure her EMG. EMG is the electromyogram, right? It is the thing, it's the electrical activity we discussed is generated by muscle contraction, right? How would you do that? You would put 2 electrodes on her arm, and then when she contracted her arm, you would see something, right? In fact, the EKG device that you're making, you can just use that for an EMG. With any modifications? No. It's the same device, right? Because you're just putting 2 wires here. Let's say you wanted to make a motion sensor. 1, 2, 3, 4. And you realize that putting 2 wires on the hand, whenever she would move her hand, you would sense that, right? And so you'd have a situation where it's like this, and then here she moves her hand, right? Motion sensor. You'll notice, this is EMG. You'll notice that in all these cases, what are you doing? You're taking 2 wires and you're putting it on her hand. That's how you would do it. In this case, this is your signal. In this case, this is your signal. In this case, this is your signal. But it's not your signal here, right? That's not what you wanted to do here, right? But you don't get to say, I'm going to put 2 wires on your hand, little sister, and now I banish EKG, EMG, and motion. It doesn't work that way, right? This is exactly how you would do these things. And so by putting these electrodes on your sister's arm, why wouldn't you see an EKG? Well, because I don't want to see it? No. It's now not your signal, it's now your noise. Since this is exactly how you would make an EMG sensor, it's exactly what you would do. You'd put, if I said measure the muscle activity in your sister's arm, you would put the 2 things here. You'd connect your device and you would see it very nicely, right? So now every time she moves her arm, every time she moves her fingers a little bit, right? It's going to contract muscles in the forearm. So you would see that as well. And so there is a noise here right? And that noise, right? Well, this is not the electrode noise, right? This is actually a physiological noise that's coming in. So we have a physiological noise, we have our electrode noise, we have a lot of sources of noise coming in here. We're measuring the voltage here. If this voltage changes, how do I know that it changed because the resistance changed versus she moved her arm or something weird happened at the electrode, the contact got not as good as it used to be before. And so I don't know when I'm looking at my V out what is driving all these changes, right? If you want, I could have added a little EKG on top of everything else, right? Right? You might have picked up a little EKG on top of it as well. So I guarantee you that if you did this, you would see a massive amount. There would be a massive amount of noise, right, that was coming into your system of complicated origin. And I don't know if I've fully satisfied your answer, but I do not think that her arm resistance, right, would fluctuate in the same way. Right.
What I'm curious saying is that the noise is a different measure and presenting itself like on top of what we're trying to measure. So that's where like our filtering is. Like, if we wanted the EMV, we would have a different filter than if we took the same data and we wanted an EMV.
Yeah, I guess what I tried to explain, perhaps yes, what you said. So what I was trying to explain is that one reason why you would have the noise of an electrical origin is because this is exactly how you would pick up biopotentials. And so these biopotentials should be coming through, right? On top of that, all the other types of noise that would be introduced at the electrode are also present. And so that's why doing this approach with DC might be very difficult. All right, that's one reason, if that makes sense. I think when I presented it, now you're digging into it, there are other things I glossed over. You know, one thing you could also do, going back to the DC case, right, is you could make this voltage bigger. All right, so I have this, let's go back to this example, and then I have a voltage here, right, that this is the live voltage, right? It's the voltage that comes out of the voltage divider, you know, when she lies. But this voltage here increases linearly with this voltage, right? So what I didn't suggest, and I'll tell you why I don't think it's a good idea, or it'll be obvious to you, is instead of using a 9-volt battery, right, use 100 volts, right? Use 100 volts here because that's going to make this bigger, right, without making these bigger. Right? But I don't think that's a good solution because I don't think you want to connect your sister to 100 volts. Because you're going to hurt her, right? And so I don't think that was the best solution. I think a good solution is to go from a DC source to an AC source. And what that will do is it will make your signal oscillate at the frequency that you put in, right? And so long, and this is a great point, so long as the noise, right, is not here, right, but is here, right, is these things, right, the noise will not be modulated. And it is a good point. So I was assuming it would not be, and I think there are reasons to think that it would, right? And I was trying to explain to you why I don't think it would be. And so now we're back to here. And all I need to do is to look at the size of the envelope. All I need to do is to look at the size of the envelope. So what I will do is I will take the signal that I have here and I will filter it. Let's see if I can use this image here. I mean, we're going sort of this way, but I have a voltage here. This voltage now is this voltage, right? And what I want to do is I want to take this voltage and I want to just let through the wiggle. That's a perfect problem, right, for a bandpass filter. I want to send it to a filter. I'm going to make it a box. This is my filter circuit. Where if I look at its gain, made it small, but hopefully you can see, as a function of frequency, looks like this. Right? And this is at the carrier frequency. And I know the carrier frequency because I picked the carrier frequency as 2022. So I'm going to make a filter that only lets 2022 through. You don't want 2022? Use 5,400. Right? It's a beautiful thing. You can set it. You can even change your mind. I want 6,000 now. You put it there. Right? And obviously you should pick a frequency where the noise isn't there. Go high. Go to 10 kilohertz. Right? Put your signal where you want it and then pass it through because we control this wiggle frequency. So you should imagine that this is really much faster than I've illustrated it here, right? Because we do want a high frequency. Okay. So this needs to be sent to a filter circuit, right? Now, how would we do that? Well, I'll tell you how we wouldn't do it. I wouldn't try doing something like, so now we're trying to take the, I wouldn't try doing something like this or, you know, however you would build like a, try to build like a passive bandpass or something. Because if I connect this to these points here, right, I've now messed up the whole circuit. Because if I connect this to this, well, I don't have a voltage divider anymore, do I? I have a voltage divider where in the middle of the voltage divider, I have 2 resistors and 2 capacitors. You can't just connect it like that, right? What I would like to do is I wish I would have a circuit, right, where I could take these voltages here, take the difference between those voltages without messing with the circuit, and take that difference and magically transport it to this location. Is there a circuit that we have that can just basically swoop in, right? Like an angel, right? Look at this, the voltage difference between here and here. Look at this difference. Extract it and make it appear here. A follower, which would be measuring 1 voltage. If I want to do, if I want to do a difference, could do 2 followers, or 2 followers would be 2 op amps. I'm lazy. I just want to use 1. I would use a comparator. Well, let's think. I want a circuit which has an input. I'm going to call it, let's say, a V positive input, and it has a V minus input. Right? I'm going to connect it to this and this point here. And I want the output, V out, to equal, right, the difference, maybe without a gain or without a gain, of V plus minus V minus. You see what I'm asking for here? I just want to get this voltage out of here. I don't want to, I'm really happy. What is that? Instrumentation amplifier. Now, I'm not saying you have to use an instrumentation amplifier. You could have used 2 followers, right? You might have thought of some way to do this, maybe because you're trying to do a threshold here, so you're thinking of comparator. Perfectly fine, right? I'm just saying here's one solution. And it doesn't require anything new. That's why I put all this here. Voltage divider, instrumentation amplifier. And I told you that for all the instruments, it's going to be either a voltage divider or an instrumentation amplifier, right? Or maybe both. So we're just going to use an instrumentation amplifier, and I know how to, and we're going to connect these points here correspond to these points here, right? You can imagine the wires, right? Coming in into these locations. And the beauty is, did this change? No, because no current flows into the instrumentation amplifier. It's like an angel that watches, extracts, but does not mess with anything. So everything I did here, my nice little sinusoidal source and my resistor and my resistor and the electrodes is untouched. I'm just going to take, and not only that, I don't just want this voltage, right? I actually want the difference. Right? Does that make sense? Yeah? And so now I've been able to extract the difference. And now I'm going to run this. I'll just do it like this into my filter circuit. And this will be a bandpass filter. Probably an active bandpass filter. Or if you want, an active low pass or an active high pass, which you are already learning how to design. And then so the final outcome here is going to be, well, what I started with. Sorry, let me redraw that. Since I had it in this color. This. I have re-extracted my signal, right? The wiggling signal. I had this. This was what was sitting here, right? And what I needed to do is I needed to strip away everything but the wiggle. And so the way I did that is by taking this voltage, the difference, and feeding that through that. And you know how to design this bandpass filter, right? You know how to design a bandpass filter because that was one of your assignments, to design a bandpass filter, right? So you already know, so we'll add that here, right? This is another tool. Bandpass filter, probably an active one. See where we're going with this? As I started when I started the lecture today, I'm not that, I mean, it's fun to talk about lie detectors because it's cute, right? But that's not the point of this lecture. The point of this lecture is to show you, and I will do this again and again as we go through the course, is that every time we come up with something new, it's not new. It's the same. It's just combinations of things that you already have, right? With the caveat that there are twists. And the main twist here is, right, is that we did this thing, right, where we had a carrier frequency. And the fancier name for this would be a amplitude modulated signal, also called AM. It doesn't matter if you don't want to remember that, it doesn't matter, but that's what it was. When you have a carrier and then the size of the carrier changes it, right? You guys ever use like an old-fashioned radio where you have to dial in the channel? And there's AM and there's FM, right? FM is frequency modulated. The AMs are amplitude modulated. It's being sent, right, as a wiggle, and the size of that wiggle is the song. And you tune in to channel 2022. How do you tune into channel 22? Well, there's a bandpass filter that just filters out the 2022, right? Whereas if it's channel 4007, you would just filter out channel 4007, and you would just get what you wanted. One more piece of it. Your sister is not lying, telling the truth, lying, telling the truth, lying, telling the truth, lying, right? It's not what she's doing, right? The signal here is not a correct reflection of her lying and truth-telling. It only wiggled so fast because we put something in. In fact, your sister is, in this example, somewhat lying, really lying, telling the truth, somewhat lying, right? It's a slow change. It's the envelope that we care about, right? It's not the wiggles. It's the size of the wiggles that we care about. Does that make sense? And so this is not quite satisfactory. I mean, it is in the sense that you could look at it and you know what's going on. But what if I said I wanted you to have a light turn on every time she lies? Okay. How do we do that? Let's go. We need a little bit more here in our circuit. What I'm going to show you is called a demodulator, okay? And it's not in our toolkit right now. It's not in our toolkit. It's going to be a new thing we'll give you. You're going to keep it in your pocket. It may come up later, it might not. What I want to do is I want to go from the pink to the purple. I have this wiggle, right? This was my output here. I've removed all the noise, so it's fair to say that this is exactly what I have with, and I want to create this signal, right? And the question is, how do I do that? You might say, well, can I filter it? You can't filter it because all of it is at the carrier frequency, right? You can't filter it. You want something that, it's almost like if you're looking at the carrier. It's almost like, I mean, what you're, I mean, you almost, I mean, what you're, this is the envelope. What you sort of want is something that would sort of, here's another color. You want it to take this value, and 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 this value. Because of those values, right? And to be clear, 0 was here, right? And so if I were to redraw those values on this chart here, I would get this value, 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 right? And that is what I want, right? This was time, this was voltage. You get the notion, right? I want a circuit that does what you're doing in your brain. How are you extracting the envelope? What is your brain doing? Your brain is looking at these ripples and it's riding, right? It's an envelope on top of the ripples, right? That's what your brain is doing. But I say I want you to make a circuit that does this, right? I want to make a circuit that does this. How would I do that? Well, what you would do is you would first start with this. Do you remember that thing? We've seen it before? What's that?
LED.
It's an LED, as we've used it before. But LED stands for light emitting diode. Let's forget about the light emitting part for a sec. Yeah, it could light up, but most don't, as it turns out. It's just a diode. So the light switch part of it is off. Now, when we introduced diodes, it had this interesting property. When the current goes this way, right, its resistance, let's say, is about 0, right? And when the current goes this way, its resistance was very, very big. I mean, that's why it only lights up when the current goes one way, right? That is a consequence. It's a light emitting, but it's a light emitting diode as opposed to a bulb, because it only lights up when current goes one way. Does that make sense? Okay. I'm going to take this signal, all right, and I'm going to pass it through a diode. AM for amplitude modulated, or for almost there. I'm going to take the VAM. Here I have a resistor, and here I have my diode. And I'm going to measure the P for post here. Okay. The question is, what's going to happen in this case, right? When the voltage is positive, right, in this case here, right? So let's zoom in. Well, here. When the voltage is positive, right, this is a positive number, right? I'm going to have a resistance. And what's this resistance? Should I do it the other way for make our life easier? Yeah. It would have worked the other way, but I just want to make things easier for us. So I'm going to put it like this. Okay. In the orange phase, this is a positive number, like 3, right? So this diode is like an open circuit, right? And so the voltage I see here, I have to maybe, let me draw it in more detail. Let's zoom in on that part right here. So it looks like this. I'm interested in this part right here. During this part, this voltage is positive. Well, the diode likes that. That's its like, come on right through, right? So the diode is going to let it through right through. Or you can think of this as the resistance of the diode is 0. Okay, what's V out? All right, let's think of it as a voltage divider. Okay, I have here 0, and here I have 1 ohm. So that's going to be 1, right, over 1 plus 0. You see, when this approaches 0, the output just comes out on the other side. Does that make sense? And so if I were to draw the output, let me draw it in purple, it's good to go. But watch what happens right here. The voltage suddenly becomes negative, right? This is a negative value, right? So current would want to go this way. Diode does not like that, right? Diode does not like current going this way. It's a very big resistance. So now I have 1 billion ohms. Well, what's the output? Well, if I have 1 ohm here, because I didn't change that, and I have 1 billion here, it's going to be 1 over 1 plus 1 billion, not very much. And so it's going to look like this. And here, right, where I'm back in the positive domain, it's going to look like this, and then back to 0, and then back up. People will call this a rectifier. If you want to know the word. What's changed? Well, whereas before the wiggle went up to a positive number, down to a negative number, up to a positive number, down to a negative number, right? Now, we only got the positive parts riding in, right? And isn't that a step towards what I wanted to do? Which is, I mean, it's not quite, but it's a step towards just picking these values out, right? Because now, what this would look like post rectifier would be, I'm not going to get all the 2, 3, 4, 1, 2, 3. I should have made these flatter. Okay, that's post diode. Right? I'm trying to create a circuit that will extract the envelope. And so the first thing I needed to do, right, was do something like this. And now I need one more piece of it. This is a rectifier. It is not a demodulator. Okay, demodulator needs one more thing. For demodulator, how would you do? Just hit a capacitor. So everyone should imagine the stages that we had here. Let me draw all our, let me draw, this was our first circuit, right, our voltage divider. Then this was our second circuit. Here was our third circuit. This would have been our fourth element in our design, okay? I know it's a little bit more steps than we've had before, but these are all steps we know. We're just putting the pieces together. The final step, which I'm just going to do right here, is one more low pass. Which could take the form of a passive, but no, you may not have to do it in passive. So I'm going to call this the, let's call this this is V4 for the output of stage 4, right? If it was clear, right? And VAM was the output of stage 3. Right, if you want to use our diagram here, right? I'm going to take this and pass it through a low pass filter. All right, and this will in fact recreate the signal. Okay. Last concept for the day. And to emphasize again, this is not a concept that is important because of lie detectors, right? This is a universal concept that will keep coming up again and again. I'm just using this example to present it. We're used to thinking about low pass filters, obviously, and high pass filters. And these are things that we build. And we have thought about them as sinusoid filters, right? That was sort of the whole basis of sinusoidal steady state analysis, right? And that is the rigorous way to think about it. But here's another way to think about it. One that is, for example, as you're doing your EKG project, is more useful. And this approach doesn't require any math, so thumbs up, okay? Thumbs up. Low pass filters, let's say, don't like, by which I mean pass, fast changing signals. High pass filters, opposite, don't like, therefore don't pass. Don't pass, to be clear. Slow changing signals. And these are very good rules of thumb to use. Let's think about an example. Let's think about EKG, right? So let's think about in the case of the EKG. Let's say you are collecting, here's the person, right, the heart, but we have noise, right? Let's say you're collecting an EKG and you're looking at voltage over time, and you see this. This is time pump 2, 3. Let's hit a gradient, right? So what you have here is obviously your signal, but you'll notice that there's this sort of low frequency noise. How do I know it's low frequency? Well, it's like slow. And slow is low frequency, right? If this was a sinusoid, it'd be a very slow one. Without doing any Fourier transform or sinusoidal steady state analysis, I know that if I want to go from here back to my original signal, oops, right? Which filter do you think would take care of this problem for me? A high pass. I would send this to my high pass. And guess what? You would be right, and this would work. Now, of course, you could say, okay, but what's the cutoff and what's that? But it would work. What if instead I saw this? I'll do it in a different scale. Okay, this is not the same scale here, right? We've kind of zoomed in on our EKG a little bit. You see your EKG, and you see that it has these very fast ripples, right? Much faster than your EKG. In this case, a low pass would take care of it. It is useful to think of a high pass filter as just like a gate. And if you are a slow moving signal, right, in this case the noise was here. Okay. A high pass filter is like a gate. And if you are a slow moving person, you do not get through the gate. A low pass filter is a different kind of gate, where if you are a fast mover, you just get blocked and you can't get through. And if you get comfortable with this approach, you will be able to just look at a signal and know whether you need a high pass or a low pass, or as it were, both. Because in reality, when you collect the EKG, shouldn't have done it that way, but what I'm trying to show you here is that in reality, the EKG includes both high frequency and low frequency sources of noise. The low frequency sources of noise are the ones that you're just watching them move around and around. The high frequency ones are the ones that you're watching with a really quick wiggle. And so in this case, we use the bandpass. Now, this is a different way of thinking than all of that sinusoidal frequency component stuff, but it's a different road to the same spot. Because in this case, what I'm saying is that the noise is made out of slow sinusoids, and therefore it will be removed. And in this case, I'm saying that the noise is made out of a fast sinusoid or fast sinusoids. And therefore I need a low pass because a low pass does not let the fast sinusoids through. And in this case, I'm saying, I got some low noises, sinusoids. I got some high frequency sinusoids. I need to trim them off on both ends, which produces the band pass filter. No math, right, in this case, but that's the concept. Another way to think of a low pass, I don't know what the right word for this is. It's a smoother. Okay, you can think of intuitively as a low pass filter as a smoother because it doesn't let the fast changes through. If you send something like this to a low pass, let's say it's a slowly going up, but then there's like a weird spike, another weird spike, another weird spike, right? If you send something like this to a low pass, the outcome is just that. Right? Because the fast things don't get through. That needs to be your intuition, right? I mean, if this was the EKG, you wouldn't want to do that, obviously, but the low pass doesn't let you, or if you sent this to a low pass, then the outcome would be this. Okay. Now this is an odd one, isn't it? Because it was a bit fast to begin with, but the low pass does this smoothing on it, right? And I don't know if I made it. Let's say you're willing to accept this for now, all right? I don't know if I've convinced you. This is what a low pass will do. If you send something like this into a low pass, it's a smoother, all right? It's a smoother. It's always smoothing, right? The low pass is always trying to kind of smooth things out. The high pass does something different, right? The high pass is like an unsmoother, right? But that's really what a low pass does. It's about smoothing things out when the things are wiggling too much. And so when this comes into a low pass, right, the low pass will smooth it. What that means is that these are pretty fast for the low pass. And so what it will do, and I'll draw it out like this, it will blur it, right? The low pass will see these fast wiggles, right? And it will blur them. It's like if something was flashing really, really fast, right? But too quick for you to see the flashes, you just see it sort of on, right? At some level, right? That reflects how bright each individual flash it was. At this point, we have gone back, which I've now deleted, to our original signal. This is the demodulated signal. Remember the goal was to pick these points out and to draw this pink line, right? At this point, we've achieved that. However, for you to accept that, you have to sort of believe, or have an intuition about how the low pass filter is this sort of smoother that doesn't like fast changing things, right? All right, we're going to leave that for today, okay? I think what I'm going to do is I'll probably send you, maybe your homework will be to just watch a couple things about modulated signals and demodulated it, so we'll sort of go back over what I said. And I'm going to have to think a little bit more about how to make this more intuitive to you. Like when I or Professor Demachowski or Professor Parra are thinking about designing filters, we actually start here. this is actually where we start. We start with, is the noise fast compared to my signal? Low pass. Is the noise slow compared to my signal? High pass. That is actually where we start. And this kind of thinking ends up being very useful. It's math free, but it's not intuition free, right? And so we'll try to figure out how to try to make that a bit more intuitive. All right, you'll get it in Par's class next semester. He'll talk a lot. Oh, ever heard of an impulse? You do that, impulse response? Anyways, you'll get a lot more of that in Par's class, but I'm going to try to set you up for that as much as I can in this class, okay?